All doing fine. So today what we are going to do is to cover our chapter 12, which is the gas and liquid equilibrium calculations. But before that, I have a few announcements. The lab number 3, all the instructions on how to work with the lab is posted online. So there are two lab instructions that you can refer to. It's posted, and you can use those to basically guides you step-by-step calculations for your lab number 3. Okay, and the due for that lab, I extended the due date, so it's May the 1st. There are two homework assignments also posted. The first homework assignment is about the density of the fluid or density of hydrocarbon calculations at the reservoir condition. Okay, that was our chapter 11 discussion last week. So the homework is posted today and it's due by next week. Okay, so the homework number 6 is due next week. And then homework number 7 also posted, which is about the gas liquid equilibrium calculations, and that's due in from 2 weeks from now. So you have homework number 6 due next week, and then you have homework number 7 and lab number 3 due 2 weeks from now, okay, on May the 1st. And we also have our final exam May 1st, and it starts, I believe it was 9 in the morning, so I'll double check the date. It is already posted in the new syllabus. So the May 1st, you will have your final exam, you will have the lab, and you will have the homework due, okay? And the reason is because your homework your exam will be the take home exam, and it's mostly based on your homework number 6 and homework number 7. Okay, so there will be 3 questions. 2 questions out of 3 will be on gas liquid equilibrium calculation and density calculation. So if you work on your homework number 6 and 7 and you feel comfortable on solving all the questions in these 2 homeworks, then you should be very good for your final exam, because as I said, questions will be very similar to the homework number 6 and 7. Okay, so make sure to go over those homework assignments and have an Excel sheet, put it in a nice format, and write the comments step by step what you need to do for every step. And send me questions. Send me if you have any questions, and email me, and then I'll try to also help you to go through that. Okay. So again, pay attention to the announcements and the submissions, and make sure you don't miss those. So today we are going to cover the gas and liquid equilibrium calculations. So far we have been talking about the gas calculations all through from the beginning till the midterm, and then we started the liquid calculations. But today, from now on, we are working on the 2 phases when you have the gas and liquid coexisting. Okay, so we have learned that in phase diagram of multi-component mixture, the 2-phase envelope, okay, defines the conditions for gas and liquid to exist. Okay, so the quantities and the compositions of phases vary at different points within the limits of the envelope. So it really depends on how much of which component is added, and depending on that, the envelope can shift to the left or right. But at every point inside the 2-phase, we should be able to find the composition of gas, composition of the liquid, and their quantities. So this is the question that we are going to address in this lecture. So in this phase envelope, there are 3 type of calculations that we are very interested in. The first is the conditions for which a mixture exhibits a dew point. So at what condition we have the dew point, okay? The next one is the bubble point, conditions for which a mixture exhibits a bubble point. And finally, quantities and compositions of the gas and liquid within the 2-phase. So I'm interested to find the bubble point pressure, to find the dew point pressure, and quantities and composition of the gas and liquid anywhere inside the 2-phase. So we are going to address these 3 questions, and one of them will be your open book questions for the final exam. Okay. So to do that, exactly like how we treated the gases, we're gonna start with the ideal liquid solution, okay? And after we learn how the ideal liquid solution works, then we are gonna make that real solution, okay? So just to remind you, the ideal solution was, in the ideal solution, the components were mutually soluble. So that was one of the conditions. So therefore, there will be no chemical interaction between the components. So the ideal solution defined as a solution where the components are mutually soluble and there is no chemical interaction, okay? So since there is no chemical interaction, therefore there is no heating effect when the components are mixed. So in this case, volume of the ideal solutions equals the sum of the volume of the components, okay? So the properties are additive in this case. So although ideal liquid solutions do not exist, their study help us to understand the behavior of the real solution. We have practiced this before. For the case of gases, again, we looked at the ideal gas and then we derived the equations and then we saw how the ideal gas behaves, and then what we did, we made a correction and then we corrected that for the real gas. So we are going to perform a very similar approach here. We're going to study our ideal liquid solution and then we are going to move to the real solution. So in the ideal liquid solution, when we have the two-phase region, right at the interface of the two-phase, the pressures are equal because the system is at the equilibrium condition, okay? Because if the pressure is different in one side, basically the pressure difference and the concentration difference will lead to some adjustment in the interface, and then everything becomes stable again. So when the system is at a stable condition, at the equilibrium condition, at the interface, the pressure in the gas phase becomes equal to the pressure in the liquid phase. So for the liquid phase, we have the Raoult's law, which says the partial pressure exerted by any component in the liquid phase is equal to the mole fraction of that component in the liquid phase times the vapor pressure of that component. Okay, so if I have a mixture of three components, the pressure that's exerted by the first component at the interface is equal to the mole fraction of that component in the liquid phase times the vapor pressure of that component. Okay. In the gas phase, however, we have a Dalton's law, which says the partial pressure exerted by any component in the gas phase is equal to the mole fraction of that component in the gas phase times the total pressure of the mixture. Okay, so we have these two laws. So the partial pressure in the liquid phase is equal to the mole fraction of component in the liquid phase times the vapor pressure of that component. In the gas, the partial pressure of every component is equal to the mole fraction of that component times the total pressure. Okay, so we have these two laws. So we are going to combine these two laws, and then we say the pressure at the interface would be the same. Okay, so I'm going to put those pressures, these two partial pressures, the same. Okay, therefore xj times pvj becomes y equal to the yj times p. Okay, and then I'm going to rearrange this such that the mole fraction of the component j in the gas phase divided by mole fraction of component j in the liquid phase will be equal to the vapor pressure of that component divided by total pressure. Okay, that's one of the equations that we are interested in and we derived. Okay, so in this case, the pressure, the total pressure, we usually know. We measure what's the total pressure of the mixture, or what is the component and the compositions at the specific pressure. So the total pressure is given. For every single component, okay, the vapor pressure can be obtained from the Cox chart. If you remember, in chapter 2, we did have a Cox chart. So if I know what is the temperature of the mixture, I can go and read the vapor pressure of all the pure components using the Cox chart. So vapor pressure can be obtained by knowing the temperature, which we usually know. We know the temperature, total temperature, we know the total pressure. So with knowing the temperature, I can read the vapor pressure of every pure component using the Cox chart. So this is known. The total pressure is known. However, I don't know what is the mole fraction of gas and what is the mole fraction of the liquid in the phase. So I have one equation and two unknowns. So I need another equation to be able to solve for y and x. Remember, here the question is, what is the composition of gas and what is the composition of liquid at any pressure, at any equilibrium pressure in the two phase. The total pressure we know, the temperature we know. So since we know the temperature, I can go to the Cox chart and read all the vapor pressures, PVJs. But to solve this question, to solve this problem, I need one more equation. And the second equation is simply coming from the material balance. So I can say if Zj is the mole fraction of the component J in the total mixture, including gas and liquid, times the total number of moles in the mixture, okay, this is equal to the mole fraction of that component in the liquid times the number of moles of the liquid plus mole fraction of that component in the gas times the total number of moles in the gas. So mole fraction of component J in the liquid times the total number of moles in liquid plus the mole fraction of the component J in the gas times the total number of moles in the gas is equal to the mole fraction of the component in the mixture times the total mole of the mixture. Okay, this is a simple material balance. Mole fraction of every component times in the liquid times the number of moles of liquid plus mole fractions of the gas times the total number of moles of gas becomes the mole fraction of component J times the total number of moles in the mixture. Okay, that's a simple material balance. So there is this auxiliary equation as well, which says the total number of moles is equal to the number of moles in the liquid plus number of moles in the gas. So the N itself is equal to the NL plus NG. Okay, the total number of moles is equal to number of moles in liquid plus number of moles in gas. Okay, so I can write this equation and use the auxiliary equation to simplify that. So how I'm going to do that? So here I learned that the Yj is equal to Xj times PVJ over P. I can write the Yj, the mole fraction of component J in the gas, to be equal to mole fraction of component in the liquid times PVJ over P. Or I can write the other way around. I can say Xj is equal to Yj times P divided by PVJ. Okay, so I can substitute either Xj or Yj using equation 12.2. And then if I do that, then I have, so here I'm going to replace the Yj with Xj times PVJ over P. Then I can solve this equation for Xj, so I can factor the Xj out. So then Xj becomes Nzj times N divided by NL plus Xj, NL plus PVJ times Ng divided by P. Okay, here. So Xj, I factor the Xj out. Xj times NL plus PVJ over P times Nj, and then I have Zj over N over Zj times N on the other side. So Zj over Zj times N divided by NL plus PVJ over P times Ng. Okay, this becomes the definition of Xj. And then I know that the summation of all the mole fractions in the liquid should add up to 1. Okay, again, that's another auxiliary equation that I know. So the summation of all the Xj's should add up to 1. So the summation of this ratio should be equal to 1. I can write this exactly the same for the gas. The summation of mole fraction in the gas should be equal to 1 as well. Okay, so I have these two equations. So in this equation, as I said, I know the actual N is equal to Ng plus NL. So I can normalize this equation by dividing the numerator and denominator by N. So if I do that, then I can define this NL and Ng bar, which are basically NL over N and Ng over N. Okay, and then I know that NL plus Ng bar becomes equal to 1. Originally, NL plus Ng was equal to N, so I divided that by N. So NL bar plus Ng bar becomes equal to 1, and then therefore NL bar becomes 1 minus Ng bar. Okay, so I can use this and rearrange this equation 12.6 and 12.7 to 12.8 and 12.9. Okay, in this equation, Zj, the mole fraction in the mixture, is always given. The PVJ I can read from Cox chart. The P is given. So the only unknown is the number of moles in the gas. So I need to iterate on Ng such that the summation becomes equal to 1. We will go over this in the next example.